did was play around with the fall speed, but what clearly is going on is the storms have very different amounts of convective activity, okay? So here's a quick summary of that previous work. The microphysics schemes yield different convective activity, including and especially at large radius. This reflects variations in relative radial distributions of hydrometeors, what kind of species are being created, how, when, and where, the fall speeds, radial spread, how these particles interact with radiation, and all these other things. So it's very complicated. The convective activity then influences radial temperature gradients, which change pressure gradients, winds, and track through the beta drift. So that's this bullet point here. So this represents basically a dynamically created asymmetry and basically impacting the system structure and motion via convection. And I can point out that Yu-Ching Wang had a paper around the same time that made many of these same points, and so they're very complementary studies in that respect. Okay, so let's move on and talk about cloud radiative feedback. So I'm going to call CRF, okay? So the plot on the left is what I showed you before, and the plot on the right is what happens when I take the same microphysics schemes and I remove the ability of condensation to interact with long and short wave radiation, okay? So it's 10 minutes already? Okay, I am in big trouble, so I'm going to talk even faster than I usually do, okay? So the main point I'm trying to make here is the fact that the very large fraction of the variability goes away. Okay, so this was an experiment that I actually did to demonstrate to myself that the cloud radiative feedback actually didn't make a difference, and it didn't quite work out that way, okay? So what we've done here is we can vary the absorption coefficients and basically change the track. There's basically one different microphysics scheme in each of these plots, and what is actually happening here is that if I change the absorption coefficients, it's basically saying I'm changing the effective size of these particles, the density of the particles, the number of the particles, and things like that. And I can change the track all over the place. Okay? Operationally, this is important because these are hindcasts of Hurricane Ike, and there are 4 tracks on this plot, and along with the best track, and this is from the German Weather Service operational mesoscale model. And the good news is one of these tracks is almost perfect. The bad news, it's the one with the simplest microphysics and the most naive interaction between microphysics and radiation. So the real bad news here is the fact that essentially what is happening is that making the model more sophisticated, in this case, actually made things worse. So why and how does this cloud radiative feedback influence the track? And I'm going to look at some symmetric response and then asymmetric response. What you're looking at here is 400 kilometers versus 18 kilometers steep, and basically this is the left-hand side here is the central axis of the storm, and it is a plot of diabatic heating, net diabatic heating, for a simulation with the same microphysics but cloud radiative feedback on, and this is off. And if I continue here, I can see that with cloud radiative feedback on, there is a much larger spread of diabatic heating than with respect to when the cloud radiative feedback is off. This plot shows you what the ice content is for these cases, and with the cloud radiative feedback on, there's more ice over a larger radial extent. This is the net radiative heating from long and short wave, and if I focus on this, I can see that I have cooling at the anvil top, I have some heating beneath, and that's missing in the CRF off case because I have neglected it, so there are some differences here. With respect to the radial wind, there's stronger radial outflow in the CRF on case relative to CRF off. And with respect to the tangential wind, there are stronger winds at larger radius when the cloud radiative feedback is on, and that changes the track through the beta drift. So I just pointed out here, this is where the winds are about 20 meters per second at 850, and it's located closer to the center of the storm when the CRF is off than when it's on. Okay. So these are basically the tracks that I just compared. So these are the cases that I compared, and one of the points here is that further improvement in position forecast may depend on getting the details of convection correct. So does the anvil spread itself? I'm going to go through this very quickly. I apologize for that, but the basic idea is I think that with the cloud radiative feedback on, the storms are larger in part because the radiative feedback makes it larger. Okay? So I wish I had time for this slide, but I don't. And so basically, let me skip on ahead here. So basically, my argument here is that what's happening is with more cloud radiative feedback, there's more diabatic heating at large radius, and that is changing the tangential winds, and that is influencing the track. Okay? And so basically what I'm comparing here are diabatic heating fields and tangential winds for two cases represented by the tracks on the right-hand side. Okay? The argument here, basically, that I'm going to make in this cartoon is that I'm going to argue that the angle can spread itself through cloud radiative feedback. This is basically represents the eye wall in the secondary circulation. Okay? I get cooling above and warming beneath due to the radiative feedback, primarily from long-wave radiation. Okay? That causes a spreading, which affects also humidity and hydrometeors, which makes the cloud radiative feedback act over a larger area. Okay? And then that could influence the convective activity at relatively larger and larger radius through this process. Now you may actually note here that this says this is cartoon number 4 of 3. I just want to point out that I'm from California, and it's clear that we have forgotten how to count. Okay, so let me finish off by showing you two simulations that are very similar, but really have a very powerful idea here. I'm going to call these simulations A and B, and it almost doesn't matter what they are at this point. This is radial distance versus wind speed, and if we look at these things, we see that the winds have almost the same tangential winds at larger radius, and from this I would expect that the beta drift is the same, and therefore the track should be the same as well. If we look at the diabatic heating and tangential wind profiles, we see two cases that are really very similar. There's differences here near the core, but out here the winds are very similar. So my expectation from this is similar tracks with relatively slow northward movement, and things didn't quite work out that way. Okay? So there are clearly big differences here between these two simulations that have nothing to do with what the winds at 200, 400, or 600 kilometers out are doing. So if I take and I vertically average tropospheric vertical velocity here, you get basically this picture. This is 150 by 150 kilometers, and this one here is, this one here is simulation A, and basically it has a structure like this with the strongest vertical motion in the northwest quadrant. This is simulation B. It has a more asymmetric structure with the strongest vertical motion in the southeast quadrant. The vectors here show the storm motion. This delta C is the difference in storm motion between the two cases, and I knew I wouldn't have time to go through a detail here, but basically we've been doing basically a PV budget very similar to what Wu and Wang did in 2000 and 2001, and basically my argument is in the case of case A, the beta drift wants the storm to move to the northwest, and the heating also